Hello everybody, I'm Zhang from National University of Singapore. I'm excited to present our work SESS, Self-Ensembling Semi-Supervised 3D Object Detection. This is a joint work with my supervisors Tyson Choi and Ginhee Lee. Given a 3D point cloud, the objective of 3D object detection is to estimate the object category and orientate 3D bounding box for all objects in the scene. Despite the promising results, most existing models require a large number of high-quality 3D labels for strong supervision. These labels are costly and laborious to obtain. Therefore, it is imperative to propose an alternative learning strategy for 3D object detection that does not require strong supervision. To the best of our knowledge, Tang and Lee proposed the only existing non-strongly supervised work for 3D object detection. However, this cross-category semi-supervised learning approach still requires a large amount of 3D labels for the strong classes. Furthermore, this approach requires 2D object detection on its RGB-D inputs. Thus, the performance is highly dependent on accuracy of the 2D object detector. In view of the potential of semi-supervised learning and the limitations in the prior work, we propose SESS, an in-category semi-supervised 3D object detection framework. Our in-category semi-supervision requires only few strong labels for each object class and works purely on point cloud inputs. Our SESS is based on the self-ensembling mean-teacher paradigm. It contains a student and a teacher branch with the same network architecture for 3D object detection. We use VoltNet as our backbone network. During a training batch, we randomly subsample from a mixture of labeled and unlabeled point clouds to get two sets of point clouds. We apply stochastic transformations that including flipping, rotation, and scaling on one set of randomly subsampled point clouds before fitting it into the student network. We concurrently feed the other set of randomly subsampled point clouds into the teacher network. The predictions of the label inputs to the student network are compared with their corresponding ground truth labels after the transformation using a supervised loss. We apply a consistency loss on the output of the student network and the output of the teacher network after the transformation. Our consistency loss consists of three terms that enforce the consensus of object locations, semantic categories, and sizes from the student and the teacher networks. The parameters of the teacher network are the exponential moving average of the student network parameters, updated by stochastic gradient descent. We compare our semi-supervised SESS to the state-of-the-art fully supervised VoltNet on the SUN RGB-D and ScanNet datasets. The red bar shows performance improvement of SESS over VoltNet on the different ratios of labeled samples. Note that with only 15% labeled data, SESS achieves a performance close to VoltNet trained with 100% labeled data. We can see that the performance of SESS as 13% labeled samples is comparable to VoltNet as 100% labeled samples on a SUN RGB-D scene. It's interesting to see that our SESS as 13% labeled samples and the fully supervised VoltNet are able to correctly detect more objects than the ground truth labels. On a ScanNet scene, our SESS is able to correctly detect more objects than VoltNet as 13% and 100% labeled samples, respectively. I have presented our work SESS that learns 3D object detection with few labeled data. Please visit our website for more information.